Good morning, students. I am Dr. Sandheep Sugadan, Associate Professor in Community Medicine, Quest International University, Malaysia. Today's lecture is on multiple binomial logistic regression using SPSS. Binomial logistic regression, often referred to as logistic regression, predicts the probability that an observation falls into one of two categories of a dichotomous dependent variable based on one or more independent variables that can be either continuous variable or categorical variable. So please keep in mind one dependent variable will be there, that is binary variable or dichotomous variable. So only two categories will be there for the dependent variable. Independent variable can be either continuous or categorical. There can be multiple independent variables. There are some assumptions for doing binomial logistic regression. First assumption is dependent variable should be measured on a dichotomous scale. It should be nominal, dichotomous. Only two categories should be there for the dependent variable. Assumption 2. There can be one or more independent variables which can be either continuous variable or categorical variable. Assumption 3. There should be independence of observations and the dependent variable should have mutually exclusive and exhaustive categories. Dependent variable categories, I told you before, dependent variable is dichotomous, right? Each category of dependent variable should be mutually exclusive and clearly defined who comes under which category of dependent variable. Independence of observation means the data should be collected from the community using a representative sampling technique. Sampling method should be unbiased sampling. So that's one assumption. So there are three assumptions. Okay. If you are opening the data file on SPSS, the steps will be like that. First you have to click Analyze, then click Regression. Then there are so many options for regression. You need to select Binary Logistic. Binary Logistic is otherwise written as Binomial Logistic. So the box appears for logistic regression. So you need to select dependent variable. Dependent variable will be categorical variable. In this case, it is presence of heart disease. Presence of heart disease, you need to define the variable as 1 or 0. 1 will be heart disease present, 0 will be heart disease absent. Then independent variables, you need to move to covariates. Covariates is the box for independent variable. In this case, there are 4 independent variables: age, weight, gender, and VO2 max. VO2 max is maximum aerobic capacity. So in this case, age is a continuous variable, weight is a continuous variable, VO2 max, maximum aerobic capacity, that is also a continuous variable. Gender is a categorical variable. So we need to define the categorical variable, otherwise computer don't know what to do with the categorical variable. So please click on categorical. We are doing this step because one of the independent variable is categorical, that is gender in this example. So we are clicking on categorical. This is for defining the categorical independent variable. So when you click on that, box appears for logistic regression, define categorical variable option. So you please select categorical variable, that is gender in this example, and move towards categorical covariates box. Select categorical variable or variables to the categorical covariate box. So it appears like that. It will show gender and within bracket it is shown as indicator. Okay. Then select reference category of the categorical independent variable based on the risk of development of dependent variable and click change. Okay, before going to next step, I will give an introduction how the gender should be defined in the variable definition in SPSS. Gender should be defined like 1 and 0. Okay, so please keep 1 as those with higher risk and 0 as those with lower risk. So in this case, outcome or dependent variable is development of heart disease. So compared to males, females are having lower risk of development of heart disease because of various physiological reasons. So in this case, we can keep females as the reference category and male as the study category. So why females are selected as reference category in this situation, because females are having lower risk of development of heart disease. In this example, heart disease, development of heart disease is the outcome or dependent variable. So in this data, females are coded as 0 and males are coded as 1. So reference category is female means first of these two, 0 and 1. 0 is the first, right? 1 is the second variable, second category. So you have to select reference category as first. Select a reference category of the categorical independent variable based on the risk of development of dependent variable or a risk of development of outcome variable, that is here heart disease, and click change. After selecting reference category to first, click change. In this example, risk of heart disease is higher among males. So females are selected as reference category. Here in data, females are coded as 0 and males are coded as 1. So reference category is selected as first. If in any case, females are having higher risk of development of outcome variable, then males will be shown as the reference category. So in this case, males are coded as 1, females are coded as 0. If males are the reference category will be last. Here, in this example, females are the reference category, females are coded as 0, reference category is first. Please don't forget to click change. If you are not clicking change, SPSS will not recognize it that your reference category is first. Okay, after that click. Okay, then logistic regression options. Okay, logistic regression options we need to select. So there are so many options here. You have to click classification plots. Hosmer, Limshaw, goodness of it, and a case-wise listing of residuals and outliers outside 2 standard deviation. then confidence interval of exponential b should be 95%. And the display should be at a last step. I will explain one by one. Classification plots will show you according to the model how many of them are having heart disease. So, how many of those really having heart disease are predicted or can be predicted based on this regression model. So, if you click classification plot, computer will give you how many of the really having heart disease are predicted by the binary logistic regression model. Why it is needed, then you can calculate the sensitivity and specificity of the model in identifying the truly diseased individuals. Second option is Hosmer-Limeshaw goodness of fit. We are generating a model. That model is known as binary logistic regression model. That binary logistic regression model will have multiple independent variables. So, we are checking if the model of including all the independent variables is fit to predict outcome variable or predict dependent variable. So we need to look for Hosmer-Limeshaw goodness of fit. Case-wise listing of residuals, computer will check how many outliers are there. Outliers are those outside 2 standard deviation that will be identified by the computer software and they will be excluded from the analysis. Then you are clicking confidence interval for exponential b. While doing logistic regression analysis, you are taking the logarithm of variables because variables are not having linear relationship. Many variables do not show linear relationship. So we are using logistic transformation. Okay, after you get the b is the regression coefficient, you need to take exponential of that. That exponential value of b corresponds with the odds ratio. So, exponential b in binary logistic regression corresponds to odds ratio of that variable. So, whenever we are presenting odds ratio, we need to present 95% confidence interval of odds ratio also. Similarly, whenever you are calculating exponential of b, you need to calculate 95% confidence interval of exponential b also. So then let us go to the these are all done in the options box. Okay, what all things? Classification plot to know how much percentage of the really deceased are identified as deceased by the model. Hosmer-Limeshaw goodness of fit to know if the model is fit or not. Case-wise listing of residual. Okay, outliers outside 2 standard deviation will not be included in the analysis. Confidence interval for exponential b, we need to select 95%. So we can get 95% confidence interval of exponential b which corresponds to odds ratio. Then display at the last step. So it will give the final step of analysis. And that is all the things we selected. Include constant in the model. Okay, that also is selected. Include constant in the model. Constant is the B0 value. Then click continue. Then click OK. Okay, this is the results. Let us go through the result. First table shows model summary. There are so many values are there, but we need to look at Nagelkerk R-squared value. The model, which included the independent variables, explained 33% of the variance in development of heart disease. So, Nagelkerk R-squared value is showing 0.330. We need to convert it into percentage. How we can convert to percentage? Multiply by 100. 0.330 multiplied by 100. So it will be 33%. So 33% of variation in the outcome variable. What is the outcome variable here? Development of heart disease. 33% of the variation or variance in development of heart disease can be explained by variation in the model, which included independent variables. There are so many independent variables added. The variation in the combination of those independent variables result in 33% of variation in the outcome variable. Outcome variable is development of heart disease. And the model fit. There is one table shown in the SPSS output as omnibus test of model coefficients. So we need to check at the third option, that's a model coefficients. Okay, what all values are given? Chi-square value for the model, degree of freedom and significance value. Logistic regression model was statistically significant. Why it is statistically significant? Chi-square value is 27.402 for degree of freedom of 4. Okay, that gives p-value 0.000, that is less than 0.05, right? So this model is statistically significant based on the chi-square test. Now we can look at the classification table. I told you before, based on the model, how many are diseased, how many are not diseased, or how many are having heart disease, how many are not having heart disease. So this table will show you, okay, presence of heart disease, okay, based on observed value. Observed value means actually they have heart disease. Okay, and out of them, how many are predicted as heart disease? So, actually 19 plus 16. So, 35 are having heart disease. And according to the model, 16 are predicted as heart disease. That means 16 out of 35. 16 out of 35 are predicted as heart disease. And according to the observation, 55 plus 10, that is 60 were having heart disease. But according to the model, only 10 are predicted as heart disease and 55 are not predicted as heart disease. So, really 65 are not having heart disease and according to prediction 55 are not having heart disease. So, regression model correctly classified 71% of the cases, those with a heart disease. So, from this table of classification plot, you can draw a table which corresponds to sensitivity and specificity. So, predicted as heart disease and the presence of heart disease. So, predicted as heart disease, yes, 16 plus 10, 26 are predicted as heart disease and out of them 16 are actually having heart disease. So, we can calculate sensitivity. Sensitivity means total diseased are 35, 16 plus 19. Out of them, 16 are predicted as heart disease. So 16 divided by 35 will give you sensitivity of the model. Specificity means true negative divided by total not disease. True negative in this case is 55. That means predicted not having heart disease and actually also not having heart disease. That is 55 divided by total not disease. Total not disease are 55 plus 10, that is 65. So 55 out of 65, that is 0.8462 are the specificity. Positive predictive value means true positive divided by true positive plus false positive. That means 16 are true positive. Why? It is predicted as heart disease and actually having heart disease. Divided by 26. 26 include true positive plus false positive. That is 16 plus 10. That is 26. So 61.54 or 0.6154 is the positive predictive value. Negative predictive value means true negative divided by true negative plus false negative. True negative is 55 divided by true negative plus false negative is 74. So 0.7432 is the negative predictive value. Okay, sensitivity of the model was 45.71 percentage. We need to convert to percentage, right? Specificity of model was 84.6 percentage. That is 0.8462 multiplied by 100. That is 84.62 percentage. Positive predictive value was 0.6154 multiplied by 100. That is 61.54 percentage. And the negative predictive value was 0.7432 multiplied by 100. That is 74.32 percentage. Now we can go through the results table. Exponential B is the odds ratio. If it is more than 1 means it is statistically significant, higher risk of development of outcome if it is more than 1. But we need to look at 95% confidence interval of exponential B also. If 95% confidence interval of exponential B does not include or cross the null value of 1, that independent variable is a significant risk factor. So we can see one by one. Age. Exponential B is 1.089. That means odds ratio is 1.089. For each 1 unit increase in age, the risk of development of heart disease increases by 1.089. Before going to statistically significant, we have to check for 95% confidence interval of exponential B. It varies from 1.030 to 1.151. It is not including 1. 1 is the null value, right? So, the exponential B for age is statistically significant. Age is a significant risk factor for heart disease. Now we can check for weight. For each unit increase in weight, maybe each 1 kilogram increase, exponential B increases by 1.006 or odds ratio increases by 1.006. But if you look at 95% confidence interval of exponential B, it varies from 0.962 to 1.051. So it is crossing the null value of 1 or it includes the null value of 1. So weight is not a statistically significant risk factor or weight is not a significant independent variable. Gender of 1. Okay. Gender are having two categories, right? 0 and 1. 0 is the coding for female and 1 is the coding for male. So gender of 1, that is being a male. Exponential B for being a male or odds ratio for being a male is 7.026. And if you look at the 95% confidence interval of exponential B or 95% confidence interval of odds ratio, it varies from 1.348 to 36.625. So that range is not including the null value of 1. So gender of being 1, that is gender of being male, is a risk factor for development of heart disease, and the risk is 7.026 times. Odds is 7.026 times compared to females. VO2 max, that is a maximum aerobic capacity, right? That is the exponential B or odds ratio of is 0.906. That means for each 1 unit increase in maximum aerobic capacity, the odds of development of heart disease reduces by 0.906. Is it significant? We have to check. 95% confidence interval for exponential B varies from 0.824 to 0.995. Both are less than 1, but it is not crossing 1. So what it means? Odds ratio of less than 1 means it's a protective factor. If maximum aerobic capacity increases by 1 unit, it gives a bit of protection to the development of ischemic heart disease. So now we can look at the constant. Constant B value is minus 1.676 and exponential B is 0.187. Constant is a situation when all the independent variable is 0. What is the value of dependent variable? Okay, that is more relevant in linear regression analysis. Okay. Exponential B is the odds ratio if it is more than 1 and a 95% confidence interval of odds ratio or exponential B does not include or cross 1, that independent variable is a significant risk factor. If exponential B is less than 1 and a 95% confidence interval of exponential B does not include or cross 1, that independent variable is a significant protective factor for the development dependent variable. How to present the result? A binomial logistic regression was performed to ascertain the effects of various independent variables such as age, weight, gender, VO2 max, that is maximum aerobic capacity, on the likelihood that participants have heart disease. Then logistic regression model was statistically significant. What it means? Chi-square value was 27.402 for a degree of freedom of 4 and a p-value was 0.0005, less than 0.0005. So that's a model was statistically significant. Model explained 33.0%, that is based on Nagelkerk R-squared value of the variation in development of heart disease and correctly classified 71% of cases. That is based on classification plots. Okay, 71% of cases or 71% of heart diseased individuals were correctly classified based on this model. And Nagelkerk R-squared was 33%. That means 33% of variation in development of heart disease was explained by variation in combination of independent variable. Okay, we made a table of true positive, true negative, false positive, false negative. Do you remember? Based on that, sensitivity of the model was 45.7%, specificity was 84.6%, positive predictive value was 61.5%, and the negative predictive value was 74.3%. Okay, of the four predictor variables or four independent variables, only three were statistically significant. What were statistically significant? Age, gender, and maximum aerobic capacity were statistically significant. Okay, so you know about gender. Males had 7.026 times higher odds to develop heart disease than females, because females or category 0 was selected as the reference category. So males, that is category with a 1, that is a score 1, coding 1, had 7.026 times higher odds to exhibit or develop heart disease. And a 95% confidence interval of odds ratio, in the table it is shown as exponential b, was from 1.348 to 36.625, and the p-value was also less than 0.05. Increasing age was associated with an increased odds of developing heart disease. For each year increase in age, odds ratio to exhibit heart disease was 1.089, and 95% confidence interval was also not having 1. 1 is the null value, right? So p value was less than 0.01. Increasing maximum aerobic capacity was associated with a reduction in the odds of exhibiting heart disease. Odds ratio was less than 1. And a 95% confidence interval of odds ratio was also less than 1. It was from 0.824 to 0.995, and the p-value was less than 0.05. So increasing VO2 max or maximum aerobic capacity was shown as a protective factor in development of heart disease according to this